Good, thank you. All right, so yeah, so thank you for coming, and thank everybody coming through Zoom. This work that is something I've been working on for a while, and I think that finally I got it. So this is about optimal online learning using potential functions. Okay, so the kind of classical problem with online is the expert aggregation. We have a binary sequence we're trying to predict. There's a learner that is trying to predict the next bit. So the learner by themselves, they can't do really much, but they have a bunch of experts that are giving their predictions. Okay, so here are the predictions of the experts. And based on those predictions of the expert, the learner decides on their own prediction. Okay, and then finally, the next bit is seen. Okay, so that is basically the ongoing game. And you don't know, so hopefully one of the experts at least knows something, can predict pretty well. So you hope to be almost as good as that expert. So the way that you, in this simple case, measure performance is simply the number of mistakes. You make a prediction, the prediction is not the outcome, and then you suffer a mistake. And the goal is that the number of mistakes that the learner makes is not much larger than the number of mistakes that the best expert makes in hindsight, okay? And so this might seem quite a natural model, but the thing that makes it different than many others is that it's adversarial. So this is basically a situation where an adversary controls both the sequence of things that you're trying to predict and the predictions of the expert. Okay, so how can you do anything in that context? So let me just give you a little bit of history. There is really a long history. So this kind of game theoretical approach to sequential prediction has been studied for more than 20 years. And the first book I know about it is this book by Schaefer and Vov called Probability and Finance. It's only a game. Then more central kind of book that has a lot of the results in the general field is this book by Cesabianchi and Lugosi. And more recently, there is this book by Khazan on convex online optimization, which is closely related to this. So what am I going to say my contribution in this work after so many works have been done? So these are just the books or some of the books, and there's of course hundreds of papers. I'm going to show something that I think I can reasonably call min-max optimal strategies. So these are strategies that it's not that there is this very small gap between the lower bound and the upper bound, but the lower bound is equal to the upper bound. And the trick to do that I kind of figured out over time is that you want to extend the game. You want to give the adversary more options. And so if you can do something against an adversary with more options, obviously you can do it with an adversary with less options. But the more options tighten the analysis. Oh yeah. Yeah, question?
In chat.
Oh, in the chat.
Yeah, I think the question is about, can you give an example of such adversary in real life?
Oh, here, this is exactly the example, right? So we all do analysis of the stock market using assumptions that the stock market is probabilistic. But in fact, the stock market is not probabilistic. People are trying to make the most money, or people are trying to figure out how to get money from you, or whatever it is. It's definitely not a probabilistic setup. Still, we kind of are used to thinking about it as this setup. So suppose that we didn't think about it as probabilistic. What would be easy and what would be hard? Well, if you have this little part that I just circled, there are two stocks that behave very, very similarly. So what should we do? We should just split the money half and half between the two, right? Because those are the ones that are so far ahead of the others that if it starts going down, we'll have time to switch. On the other hand, if it is a situation like here, then there's a lot of switching, right? So one stock becomes weak, worse than another and more than another and so on. So now kind of deciding which stock to follow or which portfolio of stocks to follow is much harder. But still, it can be done and results like this can be shown. We'll come back to that at the very end. Okay, so stock log prices often modeled as Brownian motion with drift. Okay, so this is, yeah. Okay, so this is just a question of attitude. So basically, when you go and you invest money in the stock market, are you going to assume that the stock market is benign and whatever went up will go up? Or you're going to assume something else? Here, you're not going to assume anything. So there's the value in that. I mean, of course, at the end of the day, there is, I mean, the stock market might just do a complete random walk, in which case you can show that you can't do anything. Okay, so in another way to think about this is the relationship between multiplicative weight and normal hedge. So weighted majority and multiplicative weight hedge, those have been established long ago. I think the first ones were Littleton, Warmoth at 89 and Vovk at 90. And the basic idea is that you give each expert a weight that goes down. Here I'm writing the regret. I'm kind of doing it a little bit fast. This slide is really for the veterans, right? So Manfred, this is for you. So what we're doing now is we're getting something that looks much more complicated, right? So we have this paper from 09 with the Kamalika and Daniel Su, and then more recently a paper by Luo and Shapiri that uses this kind of strange parameter, strange weighting. Okay, and the nice thing about this weighting is that it doesn't have a learning rate. There's no learning rate. You don't need to set anything. While in all of the old ones, there is a learning rate and you need to struggle with this learning rate. What kind of assumptions can I make and what should I do? Here, you don't need to do that. So in a way, this talk can be seen as how you go from multiplicative weights to normal hedge weights. But really, along the way, I found some very nice math structures. Yes?
So T is like the number of rounds.
Right.
So if I recall correctly, like you normally, for the regret bound for the normal edge, you just set the eta to be like 1 over square root of T or something to get like square root of T regret.
Right.
So isn't that like you can just set T here to get like your optimal regret bound?
No. What we will want is basically regrets that hold uniformly for any T. So the regret is, so basically the difference here is that the learning rate, you need to choose it according to T.
You choose the time horizon.
Right.
Here you don't choose.
Here,
yeah.
Initially we will, but then we'll get rid of it.
Okay.
So yeah, thanks. All right, so I'm going to do this by steps, and this is really intended for people that have no background in this, because in some very real way, this work is some work that is an extension of work that Niccolo Cesabianchi and Manfred and I and David Hembold did in 1996. So here's the very, very first case, just to show you that this is not insane. Suppose there is at least one expert that makes no mistakes. Okay. So in that case, let's say that there are n experts. One of them is perfect. So the learner's strategy is simple. You have a pool, and the pool is all of those experts that haven't made a mistake yet, right? So those are the candidates to be the right one. And you just predict with the majority prediction in the pool. That's all you do. So if the learner is wrong, then the pool has to decrease by a factor of 2 at least. And therefore, you get at most log 2 of n mistakes. Very, very simple. Now, the adversarial strategy in this setting is to split the pool into two equal size sets. Okay, that's kind of the adversary doing the worst that it can. And that also guarantees log 2 of n mistakes. So that's actually min-max. So let's look at it just in a little bit of a different way. Suppose that we have like two columns. One is the pool, and the other is not the pool. And we start with everybody being in the pool, right? And so then the expert predicts 0. Predicting 0 are the white ones, and predicting 1 are the black ones. Okay, so there are two options to the future, right? Either we predict 0 and make a mistake. So by the way, in this analysis, I always assume that the learner makes a mistake. Otherwise, it doesn't cost anything, right? So let's assume that the learner makes a mistake. If the learner predicts 0 and makes a mistake, then the 2 advance to the other set. If the learner predicts 1 and makes a mistake, then it's the complement. Okay, so these are the two future configurations. Okay. So even though this is min-max, this is just a warm-up example, I'm going to be greedier. And I want to say that I want an equalizing adversary. So I want the adversary to be such that it can always split things exactly into 2. Right? If it's integer things, then if it's odd, it can split exactly into 2. But I'm going to just assume that it can. And then you have this nice thing where the next configuration doesn't depend on what the learner chose, right? Because it's completely symmetric. So the learner can choose 1, they can choose 0. If it makes a mistake, it'll half it, and so it really doesn't matter what the learner does. If the pool size is odd, then the next pool size depends on the choice of the learner. An equalizing strategy is one where the choice of the learner is irrelevant. Okay, and we're going to do everything looking for equalizing strategy. So for that, you need something that I call divisible experts, or you can think about them as continuous experts. Basically, I'm just assuming that the experts are not just individual things, but they're a continuum. You can always break an expert into 2. And that's actually very natural, because you can think about experts being polynomials of some degree. And so the parameters that define the polynomial is continuous, and you always can split the set. Okay? So when you talk about it in this way of splitting, it's not natural anymore to talk about n, the number of experts. You can say that first you start with an expert that are 1, and then you want to reduce the fraction of experts in the pool to epsilon. Or you say at least epsilon are perfect, never make a mistake. Okay, so it's just a little bit of a change of notation.
Sorry, can I ask?
Yeah.
I must have just missed it, but like, what is the average? So what is the difference between this and the like in the set and the like initial setup without the adversary? Like, what can the adversary do?
Oh, the adversary is allowed to split experts.
Okay, so if they're an even number, they're always an even number of experts. Like, let's say the number of experts is the power of 2.
Right.
Then
you don't need it.
are all
right.
But then, so it's breaking those ties.
Exactly,
Okay.
exactly. And why am I want to do that? Because it's a little bit stronger than min-max. It's basically saying that saying to the learner, whatever you're doing, it doesn't matter. Right? Okay, so.
And this is all in this, sorry again. This is all in like this like real logical case where there is an expert that's
Yeah. So far, we're just talking about that. We'll switch from that in a minute. Okay, so what I want to give you now is a probabilistic interpretation, which I will build this example and the next example, and then I'll use it in the real stuff. Okay. So what's the probabilistic interpretation? You can think about the set of experts as the sample space, has measure 1. A single expert is just a point there. And SIW is the prediction of expert W on iteration I, or formally speaking, it's a random variable. LIW is the prediction of the learner on iteration I, so it has no W component. And OI is the actual outcome. Okay, so this completely defines the game. And I'm going to assume that LI is not equal to OI on every round, right? Because the other rounds, they just make the pool smaller potentially, but without me incurring any mistake. Okay, so then I'm defining the final random variable EIW is equal to 1 if SIW is not equal to OI, or to say differently, the expert omega errs on iteration I. Okay, and 0 if it doesn't err. So what is the pool under this definition? It's simply the set of experts such that the sum for j equal 1 to the current iteration I of the number of the mistake indicator is equal 0, right? They never made a mistake. Okay, so I'm just introducing notation, but this notation is going to be very useful. Okay, and the equalizing adversarial strategy is basically saying the probability that SI omega is equal to 1, given the past, is exactly a half. Right? That's the adversary splitting it exactly equally. Okay, so now we go another step in the abstraction. This is a little ridiculous for this very simple game, but you'll see that it will be useful later. The state of the game is basically what is this? Phi is basically the set of experts with no mistakes. That is important to realize that that's the state of the game, and it holds all of the relevant information, right? How we got to that state is not relevant. So different histories that end up with the same state are equivalent. When you kind of think about it this way, maybe it's obvious, but people have argued a lot about experts. Do the expert have memory or not have memory? So in the worst case, they have no memory. And the score, how we measure how good we are, is basically this phi of the state, it's a function of the state. It's a number that is a function of the state. And here, it is just going to be the probability of the pool. Okay?
So what is the probability of?
The probability is over experts. So it's not, okay. It's a little bit of a strange way to talk about probability, because I'm not talking here about anything stochastic. I'm just talking literally about measure theory. So I'm just saying the set, I have a set of all experts, and then I'm talking about subset of it, and the distribution over all the experts is uniform.
So it's the probability, so like psi is like some subset of like the original experts, and these subsets are uniformly distributed.
Yeah.
So in this game, it's like the probability of psi, this distribution probability of psi is uniform.
Yeah.
Overall possible psi.
Right. It's basically the measure is the measure of this bin, right? Mm-hmm. So it's the size of the bin. I call it probability because it helps.
So why is this a score?
Why? Just because here it has this property. So the property is that the learner can guarantee that the score will go down by a factor of 2, and the adversary guarantees that it will go down by exactly 2. Okay, so that's why. So basically, that means game ends when this score is smaller or equal to epsilon. So that's actually the score measures for us how close we are to the end, how much progress we've had. Okay. And this is the min-max again, log of 2, 1 over epsilon, which, as I said before, you don't really need this whole splitting thing, but it helps. Okay, so the bound itself doesn't really change, but we'll see that it makes a difference next time. Okay, so the next one, this is the work from 1996. We say there is at least one expert that makes at most k mistakes. Okay, there's an expert that makes no mistakes, just that there is one that makes it most K mistakes. Okay, that's a little bit more interesting. And we can think about it again as it's called like a chip game or a bin game, right? So we have the initial configuration where nobody made a mistake. That's here on the left. So so what do you have on the x-axis is the number of mistakes that expert made. Okay, so here all experts made 0 mistakes. And here there is one expert. There is one expert that made K mistakes. And at this point, you know that you can't make any more mistakes, right? So that's the end state, okay? All right. So again, we can draw this configurations, okay? So basically in the configurations, we have those experts that predict 0 and those that predict 1. And we have two situations, either the outcome is 1 and we made a mistake, or the outcome is 0 and we made a mistake. Each one of them will generate a new configuration, okay? And the question is, which configuration should we prefer, right? Basically, by predicting something, we know what configuration we'll get if we're wrong. Okay, so the nice thing about this game is that it has an equalizing strategy that is very much the same as what we had in the 0 mistakes. So we now have chip mass or chip probability. And now the equalizing adversary will just split each one of them exactly into 2. Okay. So in that case, indeed, if we go the prediction, the learner is 0 and the outcome is 1, or vice versa, it looks different in terms of the red and the blue, but it's really just the same configuration, right? So if we forget about the colors, these are the same configuration. So this is the situation that we like, right? That basically the learner cannot do anything. We basically tie the learner into basically, it doesn't really matter what you do, you're going to have this new configuration. Okay, and the termination condition, going back to the fact that it's divisible, is that I want that its most epsilon fraction of the experts made at most K mistakes. Okay, so instead of 1 expert, I'm just saying epsilon fraction. You can say 1/n if you will. Okay, now let's see how this interprets as a random process. So I just wrote here in small, like the same thing that I wrote before, with EI being the mistake. And the number of mistakes of expert omega on iteration I is simply the sum of the EJ, right? Number of mistakes that they made. The probability of expert with J errors on iteration I is the probability that Li omega equal to J, right? So that's basically the mass of experts that are in bin J at iteration I. And the state is the distribution over these K bins plus 1, plus a bin for everything else, okay? So that's the state. And again, the state is all that matters. We don't need to know how we got to the state. Okay, so the score in this case is the probability of good experts on iteration N. So given the current state and assuming equalizing adversary from this iteration on, right? We don't know how we got to this iteration. Maybe the adversary was worst case, maybe they weren't worst case. But our bound is based on assuming from now on, there'll be worst case. So that will basically tell us how many experts remain in the bins 0 to K, right? And intuitively, what we're trying to do, just like before, we had like a pool and we just tried to make it smaller and smaller. Here, we're trying to evict all of the experts from the 0 to K, because once we evict enough, we know that we're done. So the initial configuration is this the initial configuration for step n is how many, if I'm starting at all of them at 0, what fraction of the experts will be at the end, right there. But it's easy to calculate, right? Because it's all just half and half split, right? With just binomial distribution. And the final configuration is where we have that the state given n is simply the fraction of the examples that are there, right? So you see this, the score here is defined for all intermediate steps. Okay, so again, our strategy is really the same. We just do every expert predicts 1 or 0 with probability a half, independent of anything else. And what you get from this score is that the score doesn't change from iteration to iteration. So the score that you have in the beginning is just the score that you have in the second iteration, so on, until the end. Okay, so that's what you get. So this is the final score. And basically all these are saying, okay, what is the final score given my current configuration, right? And that doesn't change. So we have this equality throughout. Okay, but suppose that there are two configurations that have different scores, right? Because the adversary didn't do the min-max thing. Then, of course, we know which one to choose, right? We want to choose the one that would maximize the score. Minimize the score. We want to get to the end as quickly as possible, right? So if it's equal, then it doesn't matter what to do. If it's not equal, I know exactly what to do, right? I'm just going to choose the lighter side. And then I assume that the adversary will be optimal, right? So it's always kind of like, well, if the adversary is actually optimal, it doesn't matter what I do. But if the adversary at any point deviates from optimality, then I can gain from that. So that's kind of what you get. You get that the final score is bounded by this binomial tail, and that's the min-max score. Okay, so let's go back to potentials and weights to see what they mean here. So we can always write the score as a sum over bins. Okay, so we basically can just rewrite it in this way. And basically what that means is that Pij is part of the state. Okay, is an element of the state. You're iterating j over the bins j, but phi ijn is something that doesn't really depend. It depends only on the future. So it doesn't really depend on what you did. It's the potential given where you are. Okay, this is just basically all this is sum of conditional probabilities. But if you write it in that way, you basically can say, oh, each bin has a potential. Okay, so I can write the score that I'm interested in controlling as a sum, basically as the expectation over this potential. Okay, so we call this potential. It's the probability of an expert to be good at the final iteration, given that it has made j mistakes in the first I iterations. Okay, so it's in a particular place, that single expert, and okay, now we're going to play optimally with half-half. So what's the probability that it will stay in the good part? Okay, so these are, let's say that these two configurations are the future configurations depending on whether you predicted 0 and predicted 1 and made a mistake. What we okay, so in the worst case, when the adversary is worst case, these are going to have the same score. They're going to be the same configuration. So there's nothing we can do. But if they are different, then we want to know which one is smaller. Okay, so to calculate which one is smaller, this is not really complicated math. I just don't know how to make it more succinct. The basic thing is that what I'm interested is if you look at an expert and you see its score the next step for 1 and its score the next step for 0. The difference between those is the contribution to the difference between the scores. Right? So you can basically think about this value, the Wijn, as, and then again averaged, as basically the weight of the weight of that particular expert. Just a second. And this weight is going to give us an easy way to work with how to decide whether to go 0, whether to go 1. Yes.
Is this like without loss of generality for the 0 and 1? Like, are we concerned about the absolute value of this difference? Or like, so I'm just trying to make sure I understand it, I guess.
Okay.
So if this difference has a large absolute value,
yeah,
that means that the adversary is playing not optimally in terms of
right.
So
right.
like if this
And basically you would multiply this by +1 or -1. You'd multiply the sum, this thing at the end here. That's the thing that you really care about. Which one is lower? So of course you'll go to the lower,
yeah.
but if the lower is much lower, then you gained a lot. Right? And then this is breaking it up for a per expert kind of thing, or a per bin kind of thing.
So is it like sort of a measure of the deviation, like how far the distribution for that expert is from uniform? Maybe
I'll just go on right now, okay. because I think that yeah, I mean, I think that your intuitions are good, but let's just go on. Okay. Okay, so we call this one the weight, and that's the difference between neighboring potentials. So if you have two potentials, the difference between them, and it will be later the gradient, is the weight. Okay. All right, so the potential is in this case. So what I wrote before is kind of a generic thing that you could do for different games. But here for this particular game, this is the potential. It's the sum, it's the tail of the binomial distribution. And the learner chooses prediction that is smaller. And the weight is simply the difference between neighboring, and it's just turns out to be just a single term. Okay, so it's a very simple thing, which is why we call this algorithm binomial weights. So learner predicts with a set of experts that has larger weight. That's basically what it combines to. And this is how these potential and weight look like at a particular iteration. And so this is, I think, 5 iterations from the end, and k is equal to 10. And so this is the potential, and this is the weight. Now, note this is very, very different from most online algorithm. Basically, this algorithm says, if you made too many mistakes, if this expert made too many mistakes, I'm just going to ignore it, right? I'm not going to try to push it. I'm just basically going to ignore it, which is kind of strange, but that's the optimal solution. And what I think you should think about is this potential is kind of like a wave that is pushing the experts. Okay, so the experts have some distribution, but their potential, their average potential doesn't change. So it stays the same value. So if the wave comes to them, then they have to move, right? So basically this wave is the potential, and this weight is just the slope of the potential, yeah. Okay, that's how it looks.
When you make decisions, you're looking at weight, not potential.
I'm looking at both. Well, I can do it either way. I can do using the potentials to calculate the score and then see which score is bigger, or I can look at the weights to calculate the difference between the score and then see which is different. So yeah, you can do it either way. But this relationship that this basically is the derivative of this is something that will carry on. Okay, so now we're getting to more the meat. Decision theoretic online learning. So, so what is the decision theoretic online learning? It's a game that is kind of online learning distilled to what Manfred calls dot loss. Okay, so it's basically, there's no structure. So what you have is you have regrets. So you say the regret relative to, regret is basically the difference between my performance and the performance of a particular expert. Okay, so initially all of the experts have 0 and you have 0, so the regrets are 0. And we're playing here a fixed horizon game. So I misled you a little bit to say that this is not fixed horizon, but in fact, this will get rid of it at the end if we get to the end. Okay, so the learner assigns a weight to each expert. That's this game. Okay, so each expert gets some weight. And the adversary assigns gain or loss to each expert. Okay, so each expert gets a number between -1 and 1. And the learner's loss is basically the weighted loss according to the weights that the learner assigned. Okay, so the learner wants to basically put a lot of weight on things that will perform well. So that's kind of how the prediction works. And then once you have that, you update the regrets. Okay, so that basically means that you take the regret in the previous iteration for that expert and you add the loss of the expert and you subtract the loss of the learner. Okay, so that's kind of the difference. And you want to minimize regret with respect to the epsilon best percentile. Right, so that's similar to the epsilon before. And okay, so let me just show you in pictures what this game looks like, because mathematical notation is a little dense. So what we have now is basically we have all of our experts and each one of them suffered some loss. And so let's think about it as a density. It doesn't have to be a density, but easier to think. So you have all of the experts are here. Here is 0 gain. It can be gain or loss. This mass is the experts. And this is the cumulative gain of the learner. What you want is that the cumulative gain of the learner is not going to be much worse than the kind of top epsilon. Okay, so the first thing we do, we just shift the whole picture and we just put the learner at 0 and talk about regret, right? So rather than kind of having this initial 0, we kind of move along with the expert. And the state is the distribution of regret with respect to experts. So this distribution that we're seeing now, that's the state. Okay, that's basically summarizes everything that happened so far and has an impact on what will happen. Okay, so the learner, what does the learner choose? It chooses essentially a function of the regret. It can, in principle, choose a different weight for each expert, even if they have the same regret, but there's really no reason to do that. So there is a function of the cumulative regret that is the weight of the experts. And that's basically this red line. And intuitively, you want to always, put most of your weight on the best expert, but you don't want to put on the very, very best experts because those might mislead you. You need some mass there. Okay. And then the adversary, what it does, it basically, for each expert, it chooses a loss between -1 and 1. But now everything is continuous. So really, you can say that for every regret value here, you have a distribution of values between -1 and 1. Right? So that's basically the distribution of those experts. And that's the adversary chooses that any way they want. Okay, so this is kind of like the zoomed in picture. And the update goes like this. Okay, so let's say that we had the blue distribution here. And now after the experts made their move, we have this new yellow distribution. Okay, and So basically, you know, some experts did really well. And what we want is that if we now calculate, if we calculate the loss of the algorithm, which is this weighted loss of the experts, that we tracked the good ones, right? We basically want to keep holding on to the good ones. Kind of sometimes think about it as you have your horse is running and you're trying to hold on to the ones that are really strong, and the other ones, you know, let them fall back. So that's kind of what happens. And so the origin moves, right? Because the origin is the loss of the expert. Okay, so that's basically the game, and it iterates, and it stops at t, stops at some time t. All right, so the kind of bound that we're doing here is a pretty strong type. Before, you know, I set epsilon, and that was kind of defining everything, when to stop and so on. Here, I want to have a function, gr, a function of the regret, such that for every r, the probability that the regret is larger than r is smaller or equal to gr. So that basically means I'm not guaranteeing it just for one epsilon, I'm guaranteeing it for all epsilon. Okay, so I have basically for any epsilon, I have this guarantee, of course, depending on what this function gr is. Okay, so why did I come up with this? Because using potentials has been done in machine learning for a online learning for a long time. And, you know, I was working with potentials and people were saying, but we don't care about potentials, we care about regret. So then here's what I found. Let's think about something completely different, which is a mean potential bound. So we have the same state, the same distribution over regrets, but we have a potential function. Okay, so we have some potential function. It will end up being what we talked about before, but basically some function that is essentially an increasing function. And I would say that this distribution satisfies this potential function if the expected value of the distribution of the potential function relative to this distribution is smaller or equal to 1. Okay, so that's basically looks like a different thing. But in fact, it turns out that it's the same thing. So there's a theorem that it says the distribution phi satisfied regret function gr if and only if phi satisfies the average potential smaller or equal to 1 for the potential equal to 1 over gr. It's 1 to 1. So basically, in a way, it kind of says even algorithms that don't use potentials, in some sense, they can be stated as ones that use potentials, right? Because it's just 1 to 1 relative to this pretty strong condition that you want uniformly for all epsilon or for all r. Okay, question about this? Okay. All right, so now we want to analyze this game according to using potentials. But it's not at all obvious that we have strategies that would give us a potential, right, that are matching. In fact, initially we won't. But you can always define something that you can call upper and lower potentials. Okay, so I skipped here a step. So, okay, so every time we did this kind of work, we concentrate on minimizing regret or minimizing regret relative to epsilon. Now, I'm not doing that at all. I'm saying it's equivalent to doing it for potential. And potential has the advantage that you can work backwards. If you have potential at the end, you can work potential t minus 1, t minus 2, t minus 3. So you have a stronger tool to develop your algorithm. Okay, so here's basically the main tool. So I'm talking about potential functions in great generality, right? So the only thing that I'm requiring at this point is that the potential function is strictly positive, and its first and second derivative are strictly positive. Okay, so it's okay. So then you can basically say quite easily what is the best thing for the adversary to do. It's to step +1 with probability half, -1 with probability half. Just very easy to show that, okay? So here are the strategies. Okay, actually, before I talk about the strategies. So suppose that we have some strategies, okay? Some ways for choosing the weights for the learner and some way for choosing the losses for the adversary. And we're fixing those, okay? So those are fixed now. And now, if we do that, basically the whole progress of the game is completely determined, right? And what we have is that we fix a time horizon at the end, and we fix a potential function there at the end. So now we can just roll back and basically define a potential for any time, because it's simply the expected potential at the end, right? And everything is determined. Okay, so we have a lower and upper potentials, and right. So this is the definition. Okay, so this is definition of potential for a particular pair. Now, suppose that you fix just one side, and you take the infimum or supremum of the other side. Then this is what I call the upper and lower potential, right? This is basically what can a strategy guarantee against any of the opponents. Okay, so this is upper strategy, upper potential, and lower potential. And what we want to find, which we're not going to find immediately, is a strategies such that the upper potential and the lower potential will be equal. Right? That would make it min-max. But what we will find instead is simply a sequence of strategy pairs such that the gap between the upper and the lower goes to 0. So here are the strategies for this game, which I call the integer time game. Basically, the adversary just chooses loss +1 or -1 with probability half. And you see here that it's equalizing, right? Because if you do that, it doesn't really make any difference. The loss of the experts or the loss of the learner will be 0, whatever they do. And the potential, for the learner side, you have a potential that is, okay, sorry. This is the recursion this is a mistake here. This is a potential recursion for the lower potential, this half. And then we have the learner. The learner basically takes the difference between potentials. However, and that's basically the weight that it assigns. The problem is that there is a gap. So for the learner, for the adversary, you get +1, -1. And for the adversary, for the learner, you get +2 or -2. Right, so it's different. So the two potentials are not the same. There's a gap. And why do you need the +2, -2? Because the regret can change. The regret for a specific expert can change by between -2 and 2, because the loss is 1 and the loss of the master is 1. So in the worst case, you can have 2. So that's the 2. And that 2 is basically, okay, so we got something, but it's not really what we wanted. So the strategies are not min-max. It's still, it's not a bad strategy for the adversary, for the learner, to do that, but it's not min-max. Okay, so now we get to step 4, fractional time steps. So remember, we allowed at the very beginning the expert to split, the adversary to split each expert into 2, right? So here we're going to give the adversary a different superpower. Okay, so in general, the loss is between -1 and 1. And we're going to tell the adversary, you can choose any loss between, you can basically choose the range. At most 1, but you can choose smaller. Okay. All right, so that doesn't really make sense by itself because, of course, the adversary always wants to do the maximal step. So there has to be some balancing. And the balancing is that instead of in the integer time, we say ti plus 1 is ti plus 1, just the next step. In the discrete time, we say ti plus 1 is ti plus si squared. And why is that necessary? Because if you now just think about the adversary that we know and love, the one that does plus si minus si with probability 1/2, if you half the step size, you need to actually quadruple the number of steps. Otherwise, the variance would shrink or grow. So that's the critical thing, is like, even though we are making the steps smaller by 1/2, you'd think that just 2 steps would be enough. It's not the case. If you want to keep the variance the same, then you have to add si plus si squared. And then there is another thing that goes together with that, I won't get into the details, is that the loss of the algorithm cannot be arbitrary. Because if the loss per iteration is larger than si squared, then the loss in 1 unit time can be unbounded. So we don't want that, so we basically do this bound also. Okay, so these are the alterations of the game. The adversary chooses a step, and then time advances like this, and then the loss is more restricted. The adversary essentially cannot generate arbitrarily large loss. Okay, if we set si equal 1, it just looks like exactly like the original game. And therefore, okay, we gave the adversary some powers, but are they useful for the adversary? So they are. So this is kind of one of the surprising results, is if you don't have just 2 strictly positive derivative to the potential, but you have 4 strictly positive to the potential, then the adversary prefers that the step be as small as possible. So to say it differently, if you look at the potential recursion, the potential for 4 steps of size S2 is higher than the potential for 1 step of size S. Okay, so whatever size step you give, would have been better to give even smaller. Yeah, exactly. Well, it's not more; it's the most, but it's basically the natural limit. I mean, yeah, I'll say something about that if I get to it. Okay. So yeah. Okay. So. All right. So what are the strategies that we're looking at? These strategies that will become closer and closer to min-max. You basically say that the adversary makes 2 to the 2j steps, each one of size 2 to the minus j. So, by the way, this is one of the things that is kind of easy to forget about the strangeness of Brownian motion, is that the speed at which things move goes to infinity. It doesn't, basically the variance is bounded, but not the range. The range is infinite. And here is the strategy for the learner. And because now we are allowed to restrict the loss of the expert, we actually get that the range here is Sj plus Sj squared rather than 2. And what basically this says is, what we show is that this potential with j plus 1 is always higher than the potential with j. And remember, the adversary wants to increase the lower bound. So it's always better. The variance stays the same, but the more steps you make, the closer you are to a normal distribution, the better. And the other thing is that the gap between the adversary and the learner goes to zero. So the adversary wants to make the steps as large as possible to guarantee some loss, and the learner actually gets better and better in stopping him. So in the limit, they basically completely limit each other. So this is a sequence that converges to the min-max value. All right, so Brownian motion. So when we let S go to zero, the adversary strategy converges to Brownian motion. And so that is kind of one of the nicer theorems, is basically it says, if you have a potential function that has 4 positive derivatives, then the min-max strategy for the adversary is Brownian motion. That's it. You don't need to know anything else. And from that, you can directly calculate all the potentials and everything, right? All you need to say is the worst adversary can do is just be Brownian motion. Okay, so one other nice thing that comes out here is basically once you are working in that limit, then the recursion that I was describing before becomes a partial differential equation, which is called the Kolmogorov backward equation. It's basically the backward conditioning of random walk. And now you basically have an analytic expression for what are potential functions that you can use. And the learner weight is simply the derivative of the potential, just like what we said before in the K mistakes. Okay, so how to choose phi TR? Okay, so now I actually tried to choose phi TR to be min-max for a known horizon, but I failed. I couldn't do it. It doesn't work. What does work is something in a way kind of more ambitious. Basically say, forget about horizon. Let's find some function that satisfies this Kolmogorov backward equation for all time. And now you have an algorithm that you can stop at any time. Okay, so not being a big expert, but the exponential weights is a solution to the Kolmogorov equation. And then also the normal hedge. And now if you want to say, okay, so what does this buy me? In the exponential weights, if you choose eta to be log 1 over epsilon over t, then you get a bound that is 2t ln 1 over epsilon. Square root of 2t ln 1 over epsilon on the regret. If you use the normal hedge, there is only one slight parameter that I'm kind of hiding in this 1. You cannot just use t, you have to use t plus something, and 1 is good enough. And what you get from that is a bound that looks like this. And basically you have square root of t plus 1, 2 of ln 1 over 2 epsilon plus ln t plus 1. Okay, so this, if you just look at it, is worse than this, right? It has the plus ln t plus 1. However, this one holds simultaneously for all epsilon and for all t. All epsilon and for all t. So you don't need to tune anything, and the bound is almost as good as the one that was tuned. And there's no learning rate. So this is an algorithm you can run, you can stop it at any time, and you don't need to set up anything in advance. Okay. Yeah, but heat kernels usually don't go to infinity, right? These are solutions that are bounded. I have a solution that goes to infinity. So yeah, it's also heat, but it's kind of strange for heat. Okay. All right, so discrete algorithm for continuous time. So the step at the very beginning that the adversary does is kind of strange, right? The adversary wants to make it as small as possible, but it has to say something. So then it's not as small as possible. It could be smaller, right? So and it's just like not a realistic kind of thing. So what if we instead said, let's assume that it is extremely small. Let's use the algorithm for extremely small, and if it does something bigger, then we'll correct for that. Okay, so what we basically want here is a discrete time algorithm that operates in continuous time environment, right? There's the adversary is doing Brownian motion, but we can interfere only in discrete times. So we want in these discrete times to do something that would scale right. So there's an alternative description of expert cumulative gain. It's Brownian motion with drift rate and diffusion rate. So that's basically, well, if we want to go all the way to, stochastic processes, continuous time stochastic processes, then, there's Ito's processes and stuff like that we can do. But here I'm actually staying away from that. I'm just saying, okay, maybe the adversary is doing something like that, but I'm not controlling it at every point. Okay, so here is the second order bound that we get. So the weight is the first order derivative of the potential. And the drift is basically, it goes with the weights, right? The drift basically, the weights are the ones that basically guarantee that the first order term is zero. It doesn't matter at all. But then there is the Hessian, the second order derivative of the potential, and that is connected to the diffusion. Okay, so what is the diffusion? Diffusion is basically, okay, I am experts that I'm here, how much do I disperse? And it's clear that if you disperse more, then I can't hope to predict you that well, right? And so indeed, this algorithm that works this algorithm that works kind of in discrete points, but on continuous time, has the following update. Instead of Ti equal Si plus squared, which is, we don't really know this Si squared, but this is like, you do a whole bunch of steps, and then you look at the expected value of the Hessian times the diffusion, which actually makes perfect sense, right? Because our functions are convex. And so what we suffer from is the diffusion. That's basically what it says. And indeed, it gives you a completely new look at what is time, right? Because the time here, let's say that you divided the time into 3 steps. These things are cumulative, so it doesn't really do anything. The thing that matters is how much the experts go up and down, how much diffusion there is, right? For instance, just as an obvious thing, if the experts all do exactly the same thing, then there's no regret, right? Because you just do the same thing and there's no regret. So it's kind of natural thing. Okay, so brings me to the end, only 5 minutes too long. So yeah, this is basically what I wanted to tell you about, but I wanted to go back to what we started with the stocks, right? So we said that log prices can be modeled as Brownian motion, where the return is the drift and the volatility is the diffusion or the standard deviation, okay? And in fact, if you just go to standard financial thing, you basically say the Sharpe ratio, which is what people actually measure stock with, is the expected return divided by the standard deviation. So if you have basically a stock that has enormous return, but its variation is also big, then you discount it. Right here, I'm saying something a little bit different. I'm basically saying the diffusion, the variation, defines time. If you basically have twice the diffusion, things happen at half the time. So this is something I really want to explore. And interestingly enough, there is actually work on doing online learning in the context of portfolios. That's a universal portfolio, but by Cover and continuing work. But there is a big difference here. And the difference is that I don't really need the log. I can do this analysis for the prices themselves, which is a huge difference. You know, it's like, yes, you can say, in the log sense, I double my money, but then there's a constant that says that initially it was just a tenth, right? So it's a different thing. Let's put it this way: to analyze log prices than prices. Log prices are good for the long term. You know that over a long term you kind of have a multiplier, but over a short term, let's say a month, you don't want to do the multiplier. You want to actually gain some money. So that's it. Thank you. Is there anything, anybody still here? Manfred?
Yeah, we're still here.
Okay. All right. So I'm ready for questions if you want.
Yes, I only have time for one question because I have to leave. But the fascinating thing is you use this SI squared.
Right.
Square. Why is it a square and not just SI?
Oh, that's because if you have, okay, so suppose that you have this +1 -1 with probability a half-half. And now you want to make an equivalent one that would be +half -half with probability half-half. How many steps do you need in order to get the same variance? Right?
I see. And can you, you know, you made this big shift before you had sort of the halving algorithm with losses 0 or 1, and then you went to -1 and +1. Why don't you rewrite everything in terms of -1 and +1? Why
Everything
did you
is
do
in +1 and +1, everything.
What?
No, it's the range. Okay, so are you asking me why is
The
it
range
0,
count.
1 or +1 -1?
I see, the range counts, not, it's not a gain. You're not switching between gain and loss.
Oh, no, I'm allowing both. It doesn't, yeah, it's fine. There's not, it's, I mean, I know there was kind of various things about games, what is it, kind of positive games and negative games and so on. I'm just saying, no, I take all comers.
So you have an algorithm that is minimax optimal for the loss case and the gain case at the same time?
Yeah, it's the regret. It bounds the regret. So the regret is the regret. You can change the losses as whatever you want.
But the losses cannot be, can the losses be in the gain case, the losses are negative.
Right, in my case, the losses, okay, in the gain case, the losses are negative, or in the gain, it's basically the instantaneous change, change of the expert's value can go from +1 to -1. That's it.
Okay. Sorry, I have to go.
Okay.
Send me the slides, please.
Okay.
Okay, thanks.
All right.
Very good work.
Thank you. Oh, David Hembold is there. Hi, David.
Hi, Yoav. Very interesting.
Hi. Good. All right. Any questions from anybody? Wouter. Yeah, Wouter.
Yeah, so question. So if I think what I saw that happened sort of halfway through the talk is that you switched from sort of putting a regret target down to saying, let's come up with some potential, right? And you set the goal of the learner.
Right. And that's the main
in terms
theorem
of that
there.
potential at the end.
Right. The theorem is that potentials are one-to-one with the uniform bounds on the regret.
So what sort of potential functions does that sort of then motivate to pick?
Okay, I'll tell you the ideal potential function, but it doesn't work for it. Suppose you take the tail of the Brownian motion, or the tail of the binomial. That is definitely something that nobody can beat. So if you take 1 over that, you get a potential function. However, for that potential function, you get immediately infinite potential, so it doesn't work. So you want to get as close to that as possible. And I think that basically, I have to work it still out, but the optimal bound ever is basically the tail of the normal distribution. And we get close to that. Whether you can get closer, that's a great open question.
And does this allow somehow including perhaps other properties of what these experts did in the past than just their cumulative loss?
That will not be min-max. I mean, yes, you can do various
So
things.
I'm changing the rules, right? I say I want some expression to feature in my guarantee.
Right. Yeah, I don't know. I mean, the simple answer is that I don't know. This is the bound for the worst case. If you can do specific restrictions that are interesting. I mean, here's one restriction that I think is quite interesting. Suppose that the experts are just classifiers, right? They're fixed classifiers. Then I think you can do more. But yeah, I mean, you see, this is another layer. It's like if you want to assume something about the experts, why don't you just use those experts?
I'm not sure I want to assume. I want to measure something about them. Let's say.
Oh, okay. So what I'm saying, I'm saying something very specific about measuring. I'm saying what you need to measure is the cumulative variance.
Of what exactly?
Of the.
So this is a per expert quantity?
No. It's not a per expert quantity. All of this work is not a per expert. No. I mean, if you're talking about switching between experts, that's not a per expert. So no, this is a property of the whole process, if you will.
All right. Thanks.
Okay. Anybody else? Here? Yes.
Yeah, so I was just curious, like, let's say for the stock problem. So you could run like multiplicative weights update.
And people have.
Yeah.
Okay.
What is the advantage of like using like this algorithm? So there's the theoretical advantage that it models a continuous process. So like you're imagining that there's like in the background there really is a continuous time thing.
Oh no. Okay, you can do that, but I'll say much more. In my mind, the main thing is the realization that the cumulative variance is the critical quantity. That if you have stocks like in some area that basically do great things, but they also have a large variance, then you want to not go with that. And that's what people do.
I see, and like in multiplicative weights update doesn't take that into account at all.
Yeah, I'm changing one fundamental thing that I'm changing is how do you measure the regret, right? I mean, the regret is basically just something like square root of t. And so what is t? Is t just the number of steps? Or I'm saying, no, t is the cumulative variance. All right. Okay, anybody else? All right, thank you, guys. Oh, somebody? Yeah. Oh, here's Manfred again. And I can't hear you. Manfred, are you saying something? I can't hear you. All right. Thanks, guys. Manfred, I can't hear you. I would love to hear what you're saying. Oi, what's going on? All right. We'll talk later. And anybody, if you have questions, just feel free to email me or anything. Okay? Bye. Okay.